Created using Powtoon. Created using Powtoon. Created using Powtoon. Created using Powtoon. created using Powtoon.
Welcome to Teaching Physical Sciences. Today we're joined by Phil again. Hello, Phil.
Hi, Helen.
Welcome back.
Thank you so much.
And we've got Dylan back behind the buttons. Hello, Dylan.
Woohoo!
Today we're talking about teaching grade 12 electrochemical reactions. Here we go.
Yeah, it's quite a mouthful. I have to say it a couple of times inside my head. Electrochemical reactions, yeah.
Yes. And once again, you brought a whole bag of tricks.
Well, absolutely. I think toys is the key to the section.
Yeah, well, remember...
You just like toys.
I admitted and completely. I'm very much into my toys, and they help my teaching, so, it's great.
I suppose it also keeps teaching interesting.
Sure, absolutely. It engages the learners.
Yeah, well, for you as well.
Sure, keeps it stimulating for me.
Right answer, well done. Okay, remember you can talk to us using Twitter or Facebook. If you're using Twitter, use the hashtag MeScience.
Okay.
And if you are using Facebook, search for the Digital Classroom South Africa website or Facebook page at least, and then make a comment on the post that we put up there. Also, if you go to digitalclassroom.co.za/webinars and scroll below the window that you're watching us in, you will see there are two little boxes, and Dylan's going to bring them up just now, where you can just enter in a chat name and log in and then start chatting immediately. Dylan is actually logged in for us already.
Yeah, there we go. So we were busy using the science one today. So that's the one on the right-hand side. You can see that Digital Classroom is already signed in. So all you need to do is enter in a nickname and click on the big blue connect button, and you'll be able to join the science chat with us.
Oh, fantastic. So they can ask us questions live.
Yes.
Oh,
and
great.
You know what's great about this is, there are some people who aren't on Facebook or Twitter for personal reasons, and now they don't have to be in order to talk to us. They can just
Great.
go
They've
log
got a
in
voice.
And yes, they do. And remember, if you do talk to us on any one of those three channels, you do have the opportunity to win 110 Rands Vodacom airtime.
Oh, nice.
Yes. Nothing like getting something for free.
Especially on a teacher's salary.
Yes. So please do talk to us. And also remember that we have the secret code competition running, where you watch out for the secret code that will appear at some point at the bottom of your screen. Write it down. And then submit a resource to us using the email address competitions@digitalclassroom.co.za. And we'll post it publicly, and then we'll choose winners. And guess what you can win? You know this answer already, don't you?
Oh, no, I want them to guess. I want the prize for myself.
And you can win a phone or a tablet. And it's the Sony Xperia L or the Galaxy 4, a Galaxy tablet. I think it's 4. I stand to be corrected. But it's nice prizes.
The new one, the nice 10-inch one, big one.
Oh, fantastic.
They are very nice.
I told you I want that.
Yes, I think everybody does. Okay, before we go any further, shall we take a look at this book I've been reading?
Ah, fantastic, yes.
Now, you know all about this book already, but just in case you haven't been watching recently, I'm reading this book called Teach Like a Champion. Some of the steps I agree with, some of them I don't, but basically it's got 49 techniques. It says at the bottom, 49 techniques that put students on the path to college. Okay, and today's technique is technique number 14. It says students should make an exact copy of the notes on the board in their book. Okay, I'm in two minds about this.
Likewise, I've got some fairly strong opinions on this.
Oh, good. I'd like to hear yours first before I tell you mine.
Okay. I believe that sometimes it's valuable for students to take things down. I believe that this can be misused. I've been in classrooms where teachers put down streams and streams of notes, and it's a way of keeping kids busy. And I don't think that has actually got any educational value directly. In some cases, teaching kids to make good notes, though, from the board is also an important skill for university.
Yes.
Being able to summarize what's on the board or take down diagrams, it forces them to reprocess. It goes directly through their brain. They're just not taking it just auditory. It forces a motor skill. Oh,
yes.
Okay, now how do I represent this in my book? That said, it's also a way to get them to say, well, here's the symbolism. Especially in chemistry, we use a lot of symbolism, representing ions, and this is going to come up later this lesson. Representing ions, phases, and things like that are not things that can be learnt by just simply watching, reading, or listening.
Yeah.
It has to be written down by the student as well. So yes and no. If you're making them copy out large sections of the textbook off the board and their notes which could be printed out or should be printed out, there I don't think it's got a value. But especially in chemistry is definitely practicing representation, and especially symbolic. There we need to pay a lot of attention to the student's ability to write things out. So there it practices those skills. What are your opinions on this?
My opinions are that there are a set list of things that people should have written in their books.
Yeah.
And they should be there word for word in terms of a definition. But if you are writing an explanation on the board, students should be able to turn that into their own explanation within their book.
Well, to hijack a chemistry term, I like them to distill or crystallize the knowledge.
That was cleverly done. Well done. Yeah.
Yes. So I mean, I actually use that term in class. I'd like you to distill this into your own meaning, make it your own. And if you're unsure of your explanation of things, I'd like you to bring me. We'll discuss your understanding.
Yes.
It's quite a nice opportunity to engage the students.
Dylan has his hand up. Yes, Dylan.
Yes, I want to just clarify that. So you're saying that stuff on the board is good, but stuff on the board transferred verbatim to a book is bad because in that act of simply copying down, there's no mental processing that's going on?
I think it becomes mechanical. As you say, things like definitions, very often definitions, I'll give them the textbook definition, which they'll write out. Then very often what I do is I say, well, grab a pencil, and now we're going to write it out in different words. We're going to explain it from another point of view because a definition in the jargon that they use is really difficult to remember unless they've got their own version in layman's terms.
Yeah.
Very often it's less imposing. If I describe things in their jargon, very often it's intimidating to students.
Yeah.
So I tell them to grab a pencil and we re-describe it some other way.
So many people have come in here and spoken about the importance of using the right terminology to discuss things and not using jargon.
How do you mean?
Well, there's some, I suppose we'll call them purists, who say that you shouldn't use any jargon to explain anything. The learners must just understand what you're talking about. Well,
I think we've got different understandings of jargon. For me, jargon is the terminology and language and sometimes even slang associated with the section.
Okay.
So, yes, sometimes they do need to know the technical language very specifically, and it needs to be emphasized and repeated often in class, because they need to become comfortable with hearing. And it'll come up later on. There's a very big difference between talking about copper and a copper ion, for instance. And a lot of students say, well, copper was put into the solution. And if you're a chemist, you're saying, okay, well, now I'm picturing a solid lump of metal dropping to the bottom. Or I put copper ions into the solution, which makes a blue solution like the one we've got here.
Okay.
And this is why we actually need to show them physical examples of where those mistakes could be really important.
So with those definitions that you're redefining in your own terminology or your own words, you're
Absolutely.
still using the correct terminology.
They have to be. They
Okay.
have to be. You have to reinforce the correct usage of the language, especially with chemistry. There's so many terms.
Okay. Well, let's get on to the main point of the show, which
Sure.
is the electrochemical reactions. And we've got your 5-point teaching strategy. The first one says, revise how ions are made.
Okay, now this is a really important one. This stretches back to grade 10. A lot of students have got a very shaky understanding of, what ions are and how I make them. For a lot of them, just ions mean, those are the things that you make when you've got metals and nonmetals.
Yeah.
But they've remembered that that's rote learning for them. They haven't really understood that, when I make an ion out of a metal, an electron is lost from the metal to make a positive ion. Why is it positive? A nonmetal accepts an electron. And in doing that, they've already laid the foundations for reduction and oxidation chemistry, although without a lot of the terminology attached in grade 12. So it's really important for them to say, well, how do I bond a metal and a nonmetal? Back to grade 10 basics. And in doing that, you're kind of sneaking redox in the back door.
Now, what I'm hearing you say is that there is a difference between being able to give a definition and actually understanding
Very
what
much so.
ions are. And this particular step is making sure that they have that understanding.
Well, the term ion gets thrown around in redox chemistry as if it was understood, as if it was just the ABCs. And for a lot of people, I've used this analogy a lot. If you're going into redox chemistry without knowing what ions are, imagine trying to read something without knowing 10 letters of the alphabet. It's absolutely impossible.
Yes.
And that's the way that I see it and explain it to kids as well. They've got to know what an ion is, be very comfortable with ions. And there's a really nice animation that you've got in the background there that I'd like to focus on when we start talking about ions.
Okay.
Mm-hmm.
Okay, now we are talking about teaching grade. So how long should you really revise for? Is this
Okay,
like
now
a
look at-
lesson or a 5-minute or a...
I would say that the importance of this is really high, but not to spend too long on it. You're not going to reteach using the same amount of time. I would use a lesson, 2 at most.
Okay.
And here's where I start. And the most basic one is the ion which most kids know. And those are the ions inside table salt. And that is
Okay.
sodium chloride.
Yes.
So when you're starting to deal with NaCl, I like to ask kids, what is inside sodium chloride? And they say, well, there's sodium and there's chlorine. And then I say, no, there's not. And that's sort of, okay, there's something that I'm not understanding about what sodium chloride really is.
Yes.
Okay, so I start to say to them, no, there isn't any sodium, and no, there isn't any chlorine. There are sodium ions, and there are chloride ions. And they say, okay, what's the difference? Well, I explain to them further that if sodium was put in my mouth, it would explode. Okay, it's a metal, it's shiny, and it looks nothing like table salt. It's highly poisonous. It would harm me greatly. If there was chlorine in table salt, also it would be highly toxic and kill me.
That's right.
It was used as a war gas in World War I.
Yeah.
It does horrible things to people. But somehow the combination of these two elements, there's something about them which makes them safe to eat. And that for me is sort of, okay, there's something really at play here. Table
Yes.
salt's such an integral thing. Okay, so how do I make table salt? And this is where you reintroduce writing the half reactions.
Okay.
So we tell it like a story from left to right. So I start out with the sodium atom, if I want to make some table salt. So I start out with sodium atom, and something happens to the electron which is on it. Now, some teachers like to use Lewis dot diagrams, but it's up to you. You've got to feel what's happening in the class.
Okay.
Some learners really don't like Lewis dot diagrams
Yeah.
because it's got assumed knowledge from other parts of chemistry, which
Yeah.
very often are missing. So very often I like to do this like a maths equation, that sodium misses or loses an electron,
Okay.
and it becomes sodium plus. Now you can discuss with them why that's happening, and that's a great time to revise concepts like chlorine liking the electron a lot more and grabbing it. It's got a higher electronegativity.
Very technical explanation there.
I teach exactly that way. I don't want to mix it up with, there's just because there's... I find that very often chemists have got this inaccessible language.
Yes.
And if you're only teaching in chemical language, a lot of the kids they switch off. completely. But when you start to talk about the microscopic as a physical thing, it really engages them. So if chlorine is a bully and goes and steals the electron away from the sodium, they understand this.
Yes.
And then if you say, well, the desire or the want for electrons is electronegativity, then you can introduce the correct technical term. You have to do it at some stage.
Yes.
But as I say, not initially. If you run into a classroom with definitions all over the board, you're going to get afraid.
Yeah.
Okay, now the reason that the electron left the sodium was because chlorine was grabbing it. Now, so if chlorine is adding on an electron, it'll become Cl minus. And there are 2 ions. It's a great time to discuss other important parts about chemical change and representing it, because there's something not entirely correct about this second reaction.
Okay.
Chlorine is a diatomic molecule.
Yes.
As an element, it comes in pairs of 2. So you can start to discuss this with them, and you say each atom needs to join to the other one, and they come in pairs. So how many electrons would be needed in order to make the chloride ions out of them?
Yeah.
So there you start to multiply, and now you start to address issues of, okay, well, how do I get sodium and chlorine to talk to each other? If sodium only gives 1 electron, and each chlorine molecule, and it's a good time to revise those important technical terms. So chlorine molecules need 2 electrons to turn into chloride ions. How would I put these 2 together? And you can go from there. Now, these 2 processes are obviously very, very different processes from one another. I've made a sodium ion, and I've made a chloride ion. It's a good time to discuss why metals like to lose electrons, but non-metals like to gain them. And then, of course, after that, why do a sodium and a chloride ion, why are they safe and the elements are not?
So you're not just revising half reactions here, you're revising lots.
Well, absolutely. This is a good time to see if there are any problems there. This is very much like correcting spelling through reading. It's using a complex representation to quickly diagnose if there's problems in the basics. And they've got to be able to do this. There's a lot of symbolism involved in here.
Okay.
Redox is very heavy on the symbols.
Yeah.
You have to diagnose to see, well, do they know to represent the difference between, there's Na and there's Na. What is the difference between them? Why do I have to remember to write a positive? And what difference is it if I don't? Because this is probably the number one issue that we have in electrochemical cells, is that learners can't tell me the difference between Na and Na+. And they don't see the importance behind it.
Yes.
And that's really something to sit on when you're doing the section.
Okay.
Shall we move on? Or
Yes. The next step says introduce
galvanic.
Galvanic, thank you. Spontaneous cells with examples.
Okay, right. Now, this is the part where I think we should get started with some demonstrations, some bits and pieces, and some chemicals.
I'm ready.
Okay. Now, galvanic cells or spontaneous cells, these definitely need examples. Students want to know why they're being made to do such difficult tasks. They have to have the why. They have to have the hook. And this is hugely, hugely important in this case. If I show them things inside beakers, they're going to say, okay, well, why are beakers important in my life? There's colored chemicals and they live inside the science lab, and that's not relevant. Why should I care about this?
Yes.
When you start to talk to learners about tablets and smartphones, they pay attention. This is something they're using every day. They're using technology, battery-powered devices. This is the chemistry which actually governs it. Make it relatable.
John was talking about something similar last week, STS, a type of technique used with teaching where it's science, technology, and society, or maybe it's society, technology, and science, making what you're talking about in the classroom relevant to their society, their technology.
It has to be. I listened to a talk very, very recently. I think it was on one of the TED Talks, and he said from the point of view of the student had this one viewpoint: make me care. Why should I pay attention to what you have to say? A lot of teachers have this opinion that they should care because I'm saying it.
Yes.
And it's a very arrogant point of view. I don't think that's the role of the teacher anymore. We're not lecturers. We're not the custodians of all the knowledge.
Yeah.
You have to engage the students, and you have to say, well, we're equal partners. I have something cool to show you, and this is how we're going to go about it. And then you've got buy-in from them. It's going to make your job a lot easier.
Yeah.
And I would agree with John fully there. Because, I mean, this for me, I don't see this at home. I don't see two beakers connected by some funny glass piece and some metal stick inside.
And you probably won't see it again if you're not doing anything.
Absolutely. And most people never
chemistry.
will outside the classroom. So something really important is to say, well, why am I showing you this piece of apparatus? Does this represent anything that I have? And when you ask learners to reach inside their pockets and say, well, how full is the battery on your cell phone? All of them can tell you intensely because they've been watching their screens for a long time, and they say, okay, well, that many bars,
Yes.
or that percentage on the screen. Batteries and the chemistry inside there is obviously very relevant to them. They care about the chemical reaction happening in their pocket because, otherwise they can't chat to friends. And then you start to say, well, actually it's based on exactly the same concept. We're going to make a battery. And the one that's on the desk here is already functioning, which is quite nice.
Okay.
The way that I like to show them is that I've got a voltmeter connected up here. And we're going to refer back to this voltmeter in a moment. This voltmeter is telling me that this is a battery capable of producing just over 1 volt. Then if they can, open up their cell phone batteries and read the voltage over there.
Yes.
How many of these would it require to make a cell phone or power a cell phone? Then you start to grab their attention. You say, okay, well, could I actually use this to power my cell phone or charge my cell phone? The answer is yes. It's a little bit difficult, but if you have the time, I have seen teachers actually build cell phone chargers out of these chemicals. And I've bought
That's a
some.
really cool thing to do.
It is awesome.
Yeah.
You can do this, and you can show kids that once you plug it in, you can actually start charging up your cell phone, which is a fantastic thing. You can show
That's
them that there's
amazing.
energy trapped in chemicals, and that's where you get them. You're saying, wow, I'm mixing things, and
Yes.
energy comes out, and I can use the energy. And that's really cool. That's where you get them.
That's quite a thought. Now, why aren't we saying that kind of thing in grade 10? Why do we wait until grade 12?
I do sneak this in grade 10. I very often start to say, well, there's various ways of getting chemical energy into other useful forms. Now, starting to separate things into half cells very often brings up a lot of questions which can't be answered there. So I think
Yes.
that might answer that aspect. But I mean, you can tell them that if you stick two metals which are not the same into an orange or a lemon, you get electricity. That's pretty cool. There's a lot of energy trapped inside here. And, well, that in itself is an intentionally false statement,
Yes.
which we're going to address a little bit later on. But I particularly like this. I've got energy inside here, and this voltmeter is telling me how much energy I can extract just out of mixing a couple of chemicals here.
Okay.
If you have the time, connect a couple of these in series, and you can actually start powering some light bulbs, some motors. And that's really cool. Chemicals in, electricity out.
Yeah.
And that's the way to start with galvanic cells. Don't get into the half cells immediately.
Okay.
If you start with this redox table, there's a reason that I've left it off the table for a little while here. This table is full of numbers, symbols, and it's just jam-packed with so many things.
Yeah.
This is one of the most intimidating things to students. I know that you probably can't see all the symbols
I'm sure
on the screen
every
right now.
science teacher knows what you're talking about.
Absolutely. The standard reduction potential table, this is hugely important, but it's very intimidating to students. Ease them in, give them a good reason to approach, and what I say is, the hook first. Okay, start with the interesting stuff. Can I turn chemicals into energy? Oh, then you can sneak in the details. And that's my general approach here. So this zinc copper cell, there's a reason it's a standard. It works incredibly well.
Yes.
Because it's the basis for a lot of investigation. You can start to investigate. I'm going to move it into the center here, and we're going to start seeing some things. I'm actually going to write around it. Let's just make some space.
Okay. Can I do anything?
Yeah, absolutely.
Yes.
You can help me move this through here. Okay, it's from your side, and I'll move from here. Okay, all right. So what I'm going to do is I'm going to scribble on the board underneath here. I hope that the viewers watching can see from the overhead view. I've got a voltmeter here connected to the zinc on the one side, and that's with a solution of zinc chloride over here. So let me just label it from the top, because I think people are not going to remember this. So I've got zinc, and in a solution of zinc 2+ ions. Now, there again, they need to understand the difference between the zinc, the metal, and the ions inside the solution. Now, this in itself is an important discussion point, but for later on. Okay, on the other side here, and I hope that I can mess around with some of my experiments here. Just make sure that we don't spill anything. I've got copper metal.
Yes.
And copper ions.
So the copper metal is the metal that's over.
Absolutely, and this is a great point to actually drive home. I've got copper metal here, and it's this brownish solid.
Yes.
People know what a metal is. They've touched it. It's cold to the touch. It conducts electricity. And, most people know what copper metal looks like. They've seen it around their homes, particularly on windows. Ask them about copper metal. Where have you seen it? Perhaps reach into your pocket and touch some coins, which have got copper in them. What makes copper copper? Oh, it's this brownish metal. And then to address the difference between copper and the ions. Now we're saying copper ions in solution have actually got a blue color, which is quite a stark difference.
Yes.
And they need to understand saying copper and copper, it's not the same thing. It's copper and copper ions. Reinforce the language as you go. Now,
it's a good point to reinforce this point over here.
Well, absolutely, as we go. So we've got the metal ion.
Yes.
A tube in the middle, which we can talk about later.
Okay.
And it's just connecting the two sides. And then we've got zinc 2+ as ions, which are invisible.
Okay.
And then zinc metal over here. Now, a lot of people are saying, okay, well, both of them are colorless, but they're not really. One of them is a silver metal.
Yes.
And one of them is a transparent or see-through ion. Again, you can reinforce, how different a metal can be from its ion.
Yeah.
And then just by connecting these, using a salt bridge in the middle, I've got a voltage here.
So this is a bit of a random question. With lead poisoning, is that now lead ion? And please, I'm not...
Such an excellent question, and it's something I'd expect to see in a class.
Okay.
Now, with lead poisoning, you say, okay, well, does that mean that there's lead metal entering my body, or does it mean that there's lead ions entering my body? And it's actually lead ions which are going into the body.
Okay. That makes a lot more sense.
Because ions can dissolve. A metal is a solid, which, I don't usually take solids directly into my body.
Yes.
So, that's something really cool. So, I often talk to kids, you're lacking calcium in your diet. Very often doctors will say.
Yes.
If you're lacking calcium or magnesium in your diet. I get these really strange pictures inside my head, and this is a nice analogy. I picture people saying, well, I'm lacking calcium, and there's somebody sitting in front of a block of metal with a knife and fork waiting to get their calcium, and they're not really.
Yeah.
They're getting calcium ions, and they're dissolving those ions into their body, and their body will change those ions eventually into bones and teeth. And the other one is iron, of course.
Yes.
Iron is a very interesting one. It's a bit of a tongue twister. The difference between iron metal and iron ions. And that's a good one to discuss as well, because especially in breakfast cereal adverts.
Yes.
They start to say... with
9 minerals and your iron.
Yeah, absolutely. Now, that's one of the ones which is kind of interesting, because sometimes manufacturers actually do put tiny pieces of iron metal into cereal. You can actually blend certain cereals and extract the metallic iron.
I'm horrified.
You're horrified, and correctly so. So they're saying, okay, with added iron, oh no. And the one thing that actually happens is your body, through the hydrochloric acid inside your stomach, does a redox reaction.
Okay.
Now that's fantastic, because your body actually takes 3 electrons away from the iron and turns it into a form that I can use to make red blood cells, which is Fe3+, iron ions.
Okay.
So that's a cool thing to introduce when you're starting to reviews there.
Yeah, let's go back to the topic at hand.
Absolutely.
Yeah.
Okay, so now we've got this basic galvanic cell. Now this is a good time to start introducing some of the technical terms. Okay, well, why do I have a red wire and a black wire attached to my voltmeter? You might have a voltmeter that's analog, and just go through them with the basics to say, well, the standard is that red is positive, black is negative.
Okay.
What would happen if I switch the leads around? And they say, okay, well, they start making predictions there.
Yes.
Okay, so what would happen if we did switch these leads around? And you start saying, well, I connect the zinc to the other one. And what should I see on the screen? And if I do this, hopefully without breaking it, you'll start to see a negative potential.
Okay.
So there is definitely a difference in the way that you connect things. Another thing to start introducing, especially with galvanic cells, is what happens if I start to change things? the first thing that students want to do with an experiment is not to watch it, but to fiddle with it, break it, and sort of see how it works. So with that in mind, have something else at hand. Have another metal inside its ions.
Okay.
So start to say, okay, well, what starts to happen when I swap out the zinc with perhaps another metal? And here I've got some magnesium, and I've got magnesium chloride. Would I get more voltage or less voltage?
You know, this is a really good tip because I think most teachers would stop here, and it would be a good teaching technique to do this cell, but to extend it further and add another metal with its ion just makes it
more. As soon as you introduce something which a student can change, they start to say, well, how far can I go?
Yes.
And that's where you really get them, and you say, okay, well, which metal's the best? They're always looking for the best, the highest voltage. They want to make the best battery.
Yes.
And we're going to get back to the redox table in a moment. Because
that's your natural introduction to the redox table.
Yeah, there we go. So, why is one metal better than another metal? Is there a way to rank them? And that's where the table comes in.
So you introduce the need to rank them and then introduce the table.
Because a lot of teachers actually start with the reduction to potentials table, and it's not my preferred technique. It's daunting, and without these sort of experiences, it's actually meaningless.
You know, I'm getting a picture of you as a teacher over the last few things. And
I hope it's a good one.
What I see from you is that you get the child or the learner to enjoy what they're doing before you teach them how to be assessed in what they're doing. So you almost build up their confidence so that they can tackle an assessment question.
Well, this is the thing, that science is more about the doing than the equations. The equations are secondary. The equations investigate how.
So the assessment actually fails the subject in a way.
A lot of this is a systemic problem. All of us, because of time considerations, I know that it would be nice to teach every section this way, but time constraints are a very real problem for science, maths, and any other teacher. So a lot of people say, okay, well, how do I get them to the test and get them passing first?
Yes.
And in doing that, we all sort of fall back into lazy patterns. We have to constantly go back and say, no, well, this is not the best practice.
Okay. Sorry, I've taken us off topic again. Let's go back to this.
All right. So, I mean, I asked them to make predictions. We've got zinc and we've got magnesium. Now, I'm going to replace the zinc, and I introduced the word a half cell because I have an entire cell, and obviously I'm going to take away half of it.
Okay.
So you start to sneak in the terminology. So we say, okay, now we've got a zinc half cell. Let's disconnect the half cell, and let's replace it with one which has got magnesium. And this does require a little bit of care because it can make a big mess. I can see you sort of going away from me there.
Lean back.
Okay, and what we'll start to notice is immediately that magnesium is making 1.71 volts. I have a measurable difference between two things which look almost identical. I have a gray metal inside a clear solution in both cases. Now, inside a student's mind, they're saying, well, clearly magnesium does something better than zinc.
Yes.
And then you start to play around with combinations. There's quite a few of these that work particularly well. Iron is a very nice accessible one because all you need is a rusty nail. So a rusty nail works particularly well inside a solution there. Now, at this point, you start to say, well, is there a way to predict how much voltage something is going to... So now you're looking for an undercurrent. You're looking for how does this actually work? I know that playing around with them experimentally is fun, but is there a way to teach or at least investigate a method?
Yeah.
Yeah.
Would you say, Phil, that the playing around is fun, but then what you need to start kind of driving learners towards is to find the pattern?
Well, usually they're actually pretty good at driving you.
Oh, okay.
Well, this is the thing. Just their natural curiosity, they're saying, okay, well, is there a way of predicting? Is there... I mean, they learn this in maths a lot. Look for the pattern. How do I get from one thing to the next? How do I get from zinc to magnesium and know that the voltage is going to go up?
Yeah.
And can we continue the trend by constantly changing metals?
Yeah.
Which is quite nice. And that's where the ranking system, this table, comes in. So now is the time to start saying, okay, well, here we've got a very real experiment. Is there a way to predict that zinc and copper would give me roughly 1.73 volts? And that's when to introduce this table, saying, well, this is kind of like a score sheet for metals and non-metals. The metals are ranked on the one side, whereas the non-metals are ranked on the other side.
Okay.
And start to discuss with them, why are they ranked on opposite sides? Why are the better metals up at the top here, and why are the better nonmetals down at the bottom? They are the better reactants. And then you introduce the word better reagents, because that's a word that they often get used in testing, but I very often found that it's never been explained in class. I've got grade 12 learners that say, well, they've used this word reagent, and it sounds like something that the CIA is sent into a
Yes.
So now, an oxidizing agent or a reducing agent, you need to start introducing these ideas and separating them from oxidizing reactions and reducing reactions. And that's one of the pressure points that we're going to discuss.
Okay. On that note, we've got 25 minutes left, so let's move on to the next point.
Absolutely.
It says calculate and predict cell potentials. Now, we've spoken about that, haven't we?
Okay, so we've started there. We've planted the seed. So is there a way to predict that there is 1.71 volts here? And I like to just give this sheet to kids and say, I want you to find how I got 1.71 volts out of here. Is there a way that you can perhaps find the relationship between copper and magnesium? So they start to run around on their sheets. And my advice to you is when you've got these sheets, you're going to go through a lot of them. Either make a lot of photocopies, or there's actually a better method for students, is to put one photocopy inside a plastic sleeve. And then on the surface of the plastic sleeve, they can highlight the reactions that they want, and they can do it over and over and over again.
Yeah.
You're not making 1 million copies and wasting a lot of paper. It does get expensive because each example uses one of these sheets, and that gets really pricey.
Sure, yes.
So, I mean, this particular example, if you ask learners, well, what is the relationship between magnesium up here, zinc down here? And then you start to say, okay, well, is there a relationship between those metals? And then you start to take a look at copper down here and copper ions and the ions of zinc and magnesium. Now, there's some arrows on the side of this table which are actually really nice for guiding which ones are going to be the best. And if you give them a little bit of time,
Yes.
they'll quickly figure out that there's some numbers which are next to these metals. And if you start combining those metals in a certain way, you'll start to get the voltages which you see in the experiment itself.
Yeah.
And the minute they can start predicting this, they starting to say, well, what if I use this one and that one, and this one and that one? And they start to see that they can get bigger and bigger and bigger voltages.
And of course, by discovering that themselves, they've formed the connection
Absolutely.
in terms of knowledge, and it's stronger.
Great. And again, back to the cell phones.
Yes.
One of the things that I love them to do is grab their cell phone battery and read the voltage on the back. And then read the label. It says lithium ion. Why have they made a lithium battery inside your pocket?
Yes.
And you point out that lithium is right up at the top of the table.
Wasn't it a South African who developed the lithium-ion battery?
It was involved, yes. Originally, there was a Zebra battery project, which had the offshoot there, yes.
Okay.
Well, this particular one, you can start to see, your lithium is the best metal. So
Yes.
why wouldn't we use the best metal for use in mobile devices? It's obviously got other advantages as well. Very nice light metal as well. And you can discuss I know that it's no longer in the syllabus, but issues of battery design are fairly important.
Yeah.
Because you can ask them, well, your choice of metals, what is the cell potential which can be made?
Yeah.
And this table actually becomes really empowering to them because it gives them a way of predicting, how would I make the best battery? And their initial response is, well, then why can't I take some fluorine, which is right down at the bottom here, and some lithium right up at the top here? Those would make the best battery, and that would make over 5 volts. And then you start to say, well, it's not practical to carry around fluorine because, it's incredibly dangerous gas.
Yes.
So, start to discuss these. It brings up interest and it gets them asking questions.
Yeah. Okay. The next point says reintroduce electrolytic. Electrolytic?
Yeah, electrolytic.
And non-spontaneous cells with examples.
Okay, so this is your electrolytic cells. So you're also going to be referring back to this table, but
Okay.
in reverse. And that's not going to make much sense unless you start with the examples.
Okay.
So now you can explain to them that reactions can go in a spontaneous way. In other words, they would go a certain way without any help. They would start themselves, just like the zinc copper or the zinc magnesium cells that we've made over here. For instance, if we made a lemon battery, and if we've got a little bit of time at the end, we'll discuss that. Now, the electrolysis, I very often like to start with the electrolysis of table salts and the electrolysis of copper chloride. So I'm actually going to
Okay.
do a little bit of double duty here. So I'm just going to leave that on its own on the side. And we're actually going to electrolyze some copper chloride. Now, copper chloride is something which is very nice to electrolyze because the cool thing about electrolysis of this is it actually separates into copper metal and chlorine as a gas. You can see that electrolysis separates elements. It's a way of chemically changing things back into the elements.
Okay.
So we're going to do just that.
I'm going to change chlorine back into a gas.
Absolutely. We're actually going to change it into the gas. I'm not going to make too much because I care for our health.
Yes.
Okay, so there's a lot of clutter on the table. I'm just going to clear this out of the way at the moment.
Okay.
Now, when you're doing electrolysis, it's really important for you to start emphasizing that there's energy changes going on.
Okay.
The energy change that we had in the galvanic cells was we put chemicals in, or chemical potential energy, and got electrical energy out.
Yes.
Now, here we're going to reverse the process. So the reactions also are reversed. So what we're going to do is we are going to start plugging things in. And one of the things that I like to plug in is a spoon. I'm going to try to do this without bumping the microphone too much. We're going to do electrolysis with a carbon rod and a spoon. And I'm going to shift this across here.
Okay.
We're going to do that one next. And that's our last point. The electrolysis of copper chloride, I would say, is an absolute need because it shows why we do electrolysis, how it's useful. And this one does double duty because this is one of the applications that they actually need to know. They need to know that if you electrolyze copper or some metal salts, very often you can actually get the metal to form on the surface of another metal. So I'm going to use copper for the one electrode.
Yes.
And I'm going to use a spoon for the other electrode. I don't suggest a spoon that you don't particularly like or don't need anymore.
Or you do suggest a spoon.
Well, spoons are particularly nice because they're coated nice and evenly. You can use anything which is metal and conductive.
Okay.
I've even seen a leaf being used. If you use a solution of silver nitrate, you'll coat the leaf in silver. It's very beautiful. But it's an expensive experiment, and not everyone can do that.
That's very interesting.
So what we're going to do now is we're going to connect the positive electrode to the carbon, and we're going to connect the negative to our spoon. And hopefully what we see, if we switch on our power pack, this is just a normal sort of benchtop power supply. And what we start to see is a slow but gradual change. If we get this to work. There we go. Right, what you'll start to see, and it's a good idea to rotate your spoon around as you do this, is that the color of your spoon will actually start to change. Now, you can see a gas being formed at the one electrode.
There are bubbles coming up, yes.
There are bubbles. And if you're close enough to smell this, and I invite the students to smell this, obviously using correct technique, they should be wafting this towards themselves. A lot of them would correctly identify the smell as the smell of bleach or Jack.
Yes.
Or pool chlorine. Now, if you can start to see, the color of our spoon is actually starting to change along the edges. I'm actually starting to see that the spoon has now got this.
Oh, yes, it's gone like
can you see there? Okay, so there we go. We can
it's
start
got
to
almost
see.
a copper-type look to it.
Well, it should. It's got an actual layer of copper on it.
I must be honest, I expected it to come out blue.
Okay. Well, I mean that's great. A lot of students are saying, well, I'm putting it in something blue. Why is the spoon not blue? Now, I've changed copper ions into copper metal. And if you carry this on, this is a nice experiment to leave on in the corner of a classroom. And you'll start to notice that you actually get this really beautiful layer of copper that starts to form. So I'm just going to leave that for a second while we talk.
Okay.
And we're going to start to see a layer of copper building up and up and up. And you can actually sort of scrape it off, and you can actually see copper metal being formed, which is really nice.
Yeah.
So now discuss this with them. I've changed copper ions into copper metal. I've changed chloride ions into chlorine atoms, and especially into chlorine molecules. And that's the gas that I'm seeing. We can smell the gas. We can see the metal. It's very, very physical.
Yes.
And this is one of the applications that they need to know. This is electroplating. Taking a metal ion and putting a coating of one metal over another. This often happens with gold, for instance.
Yes.
Gold-plated items or chrome-plated items. Make it real for them. Why would I want to do this? Why would I want to put one metal onto another?
Yes.
Well, the one metal is less valuable, and obviously a thin plating of the other one gives it the appearance of being much more expensive. So here, now that we've left it a little while, you can actually start to see the division line between
That's quite remarkable.
the unexposed spoon and the newly formed copper. Now, also talk to them about this. Now, you can actually rub this copper off quite easily with your finger, and you can start to see it there as that brownish metal. Now, start to say, well, and how would you get these two metals to stick to each other? How would you actually go into spoon manufacture where you had to do this? I don't know if you can smell this in the studio. It smells a little bit like pool chlorine or Jik.
Yes.
And discuss that with them. And the other very, very important one that has been kept inside the caps is this one over here. Now, this is probably one of the worst answered questions inside the matric exam, and that is the Chlor-alkali process, which is an application of electrolytic cells.
Okay.
What I've done is I've got a solution here with some universal indicator, and we are going to do the electrolysis of salt. And just to show them, I've asked Helen for some salt over here.
And it's normal table salt.
It's normal table salt, and we start to sprinkle a little bit of salt inside here. And it's a really nice idea to go to the FET website and take a look at the animation and show them what actually happens when salt dissolves inside a solution. When you're dissolving a salt inside a solution, the sodium ions and the chloride ions are going to separate. So that solid down at the bottom will actually begin to separate. Now, while I'm doing this, so as I do this, and I think Helen's going to do the shaking on the screen in a moment or two.
Yes, just pulling it up.
Yeah, there we go. Something quite important and really, really difficult to understand for them is why am I actually putting this into a solution? It's to make it conductive. I'm going to divide it into two half cells using a little piece of paper or cardboard. And what we've actually done is we've actually created a very simple diaphragm cell. We've separated it into two parts using a porous membrane. I'm going to connect a positive to the one side. And we're going to see something quite cool over there. And a negative to the other side. And they've got to predict what you expect to see. And when I switch this on, we should start to see something as soon as we've got our ions dissolved in solution. This may take a little while. I think the salt is not dissolving in the cold water as well as we should. It's starting to work now. What you should start to see after some time is that there should be two gases starting to form. I think I'm going to add a little bit more salt as we go. While we do that, I think we should look at the animation.
Okay. So I've got it up on my computer screen.
Okay, now as the salt goes inside there,
I'm shaking.
There we go. So the sodium and the chloride ions are starting to separate, and we start to see that they're now free-flowing. They're allowed to move around inside the solution. And this particular cell that I've decided to make is running electricity through that mixture. So this mixture over here is going to electrolyze that. So we're going to attract the positive ions to the one, and we're going to attract the negative ions to the other. Let's just see if this will work now. As with anything, sometimes they don't work as well as they should. I think we're starting to get some electricity flowing through there.
Okay.
Okay, and what you'll start to see, there we go. You're starting to see that there's a color change happening on the one side.
It's going darker.
Yep, it's going darker on the one side. We're starting to see a blue color at the negative electrode. And
it's going very blue from this direction onto
absolutely.
the paper. You can see it quite clearly.
Which is really nice because one of the products of the chlor-alkali process is an alkaline material. And that's sodium hydroxide. We're actually producing sodium hydroxide here.
Okay.
The color is being produced by a universal indicator.
Well,
No.
can you just move that just a wee bit as we get the overhead camera? It shows it beautifully.
Yeah, absolutely. Okay, so you can start to see the separation between these two colors. So I'm starting to produce a blue color on the one side because I'm producing an alkaline base on the one side.
Yes.
And on the other side, I'm producing a mild acid because I'm making chlorine gas. Now, chlorine gas does two things.
Yes.
I can see you're starting to get a little bit nervous here. Okay, chlorine gas dissolves in water to make a mild acid, so you should start to see the acidic colors coming out, the warmer yellow or orange colors.
Yes.
But then the color starts to disappear as well, which is the other useful aspect of chlorine. Chlorine is very good as a bleach. It removes color altogether. So it first goes yellow and then vanishes altogether.
Yes.
So it's really nice. You can actually start to see where these products are being made. Now at this point, it's really good to see that I've got my positive connected to the one. Why is it going a certain color there? Negative at the other side. Why is that going over there? Why am I making sodium hydroxide at the negative? Why am I making chlorine at the positive electrode? I'm make this real, because this very often stays as a picture on a teacher's board and is inaccessible. I think we're probably going to have to get back to our pressure points. I think we're running out of time.
Yes, we are. Is there anything more you want to say about this simulation?
Now, in this simulation, it just really sort of drives home that first point of identifying what actually happens when ions in solution. Ions are free to move around, and this is the way that electricity is conducted through a solution.
Okay.
It's different to metals because metals allow electrons to move around, whereas inside solution, ions can move around. It shows that
and
motion.
Actually seeing it physically.
Well, that's the microscopic representation. They're just seeing symbols on a board, and it's very dry, it's very abstract.
Yes.
Now, what we've got over here is a saturated sodium chloride solution. And, you can start to ask them, what's actually happening inside there? Why are they green and why are they pink ions?
Yes.
Why are they different sizes? So that's back to the grade 10 formation of ions. Always revising back to those basics, because you should never assume that they know those.
Yeah. Okay, 3 pressure points.
Yeah, and these are really important. Okay, so when you're starting to take a look at the pressure points, this is the one thing. Please don't assume that they remember everything from grade 11. The grade 11 stuff is very often shaky. They might have been with a different teacher. They might have come from another school. I very often reteach the basics of redox chemistry, taking about 2-3, because this entire section relies on the basics of redox chemistry. You cannot assume that they know how to use the table or write a reduction or oxidation reaction. It takes quite a while. You have to address a lot of problems and shortcomings.
Yeah.
So that for me is one of the most important things. Never assume there.
Okay, the second point, place special emphasis on details such as charges, phases, and language used.
This is a big shortfall. When we find the exam answers in exams, obviously that's where they would be. When we find the answers in exams, people have obviously started to confuse elements, ions. They're not sure of the differences between all of these things. As I've said, what is the difference between copper solid and copper 2+ aqueous?
Yes.
I mean, those are really abstract terms unless they say, okay, well, one is a brown metal and one is a blue ion floating around inside a solution. The macroscopic, just having something to hold in their hands, is very, very difficult for them to link up with a symbolic unless you actually say, well, this is Cu2+, aqueous. This is Cu metal, which is a solid.
Yeah.
And emphasis on the phases, emphasis on the charges as well. So making sure that they're comfortable with the language is really, really important.
Yeah. I wonder.
Mm-hmm.
Okay, so obviously working here, we work a lot with videos.
Yes.
And making notes on videos and things like that. I wonder if it would be worth having a clip of the iron in a solution versus the metal and have the formulae on the bottom.
Oh, yes. Especially, I would say that it's very, very appropriate, especially for grade 10 level. The grade 10 level, just saying that this is an iron, this is a metal, and then again for grade 12 revision, it would be useful to go back and revisit those.
And do all of the metals and the ions, a comparison, as much as possible.
Well, it's difficult to cover them all. Just the establishment that there is a very big difference between.
Yeah.
Copper's a really nice one because it's so strongly
very
colored.
Obvious, yes.
It's very beautiful as well. I like the blue color. It's a brown metal, which is unusual, so it really sticks out in their mind.
Yeah.
Most of the other metals do exactly the same thing as magnesium and zinc. Most of them are
okay,
silver
so it's
metal.
pretty boring.
It doesn't really stick out.
Yeah.
The other, some of the transition metals really do stick out. Like iron has got an orange color. Manganese can be a nice, beautiful pinkish purple.
Yeah.
So use the ones which really stand out, just to drive the point home.
And just a couple of examples. Maybe
Absolutely.
take photos of them and put them up on your board or something.
Yes. Colors of ions are not directly asked in the syllabus, but useful.
Yes.
The solution went blue. Could it be copper?
Yes.
Is the initial sort of conclusion. Then you start to give them that sort of background.
Okay, and your last pressure point says try to separate similar terms, oxidizing reactions from oxidizing agents and vice versa.
Now, there's a lot of confusion that goes on. And that difference between oxidizing reactions, and let me just give you an example of how a student hears this. Reduction occurs when you have an oxidizing agent.
Yes.
In English terms, that makes no sense.
Yes.
It makes absolutely no sense. I thought you said it was a reducing agent, so why is it not reducing? You have to sort of seed through all of these problems and filter through. So, a reducing agent is called a reducing agent because it causes something else to undergo reduction.
Okay.
An oxidizing agent is something which causes something else to undergo. And you've got to do this with examples.
It's kind of like the Terminator who terminates other people, but
Absolutely.
is not.
Well, I mean, that's quite a lethal example. I usually use sales. A sales agent causes a sale to happen. They're not doing the buying. They're not doing the buying themselves.
Yeah.
So that's one of the ways that I say, well, an insurance broker or an insurance agent is not interested in buying the insurance for themselves.
Yeah.
They want you to have the insurance. And it's the same as, an oxidizing agent wants the other chemical to be oxidized.
Yeah.
So an agent is there to make something happen, not to undergo that change itself. So, those terms are so commonly mixed up. And very often there's little shortcuts that they're taught that don't really teach them understanding. I know there's one that teachers often say that the agent is always opposite to the reaction.
Yes,
I don't
that
like.
sounds familiar.
Well, the reason I don't like, let's rather say the reason it's common is because it's easy. I know that an oxidizing agent, if you flip it, it becomes a reduction reaction.
Yeah.
But it hasn't actually taught me why, which for me is a really big problem. There's no mechanics, there's no understanding in there. It's just a way of remembering something. And I'd like to try and avoid that if possible.
Now, you do have a list of good ideas.
Okay, let's see if we can get through these in the time frame.
Well, we've got 3 minutes. I'm sure we can. Use
Sure.
many practical examples.
Mm-hmm.
Yes.
Okay, so we've started to put these into play here. I've gone through about at least 3 or 4. Something that we can actually do while we wait is this one I particularly like, and this is the making of a lemon battery. And if you stick some copper and you stick some zinc inside a lemon, you can actually produce very similar voltage. And I'm going to grab my voltmeter over here, and we're going to test the voltage that can be produced with lemon battery.
Okay.
Now, there was recently a news report of some girls in Nigeria that produced a battery that ran off urine, which is not something that you'd probably handle inside a lab. And
yeah, I can see complaints coming
there's
from
some
that
difficulties inside that, and also there's some bad science in the reporting. Now, I don't like calling this a lemon battery because the lemon is not actually the source of the electricity or the energy.
Okay.
And that's a good discussion to have. So if I connect these, I get a reasonable amount of voltage. Let's just make sure that we're getting the correct terminals over here. I'm actually getting almost 1 volt, but it's less than we got when they're inside their own solutions.
Yes.
Now, if you start to actually diagnose what's going on inside here, it's actually the energy that was invested in making this plate of zinc. The zinc dissolving is where the energy is actually coming from. These two metals don't actually mind what you plug them into. If you plug them into an orange, for instance, you will also get electricity. They don't even have to be citrus fruits, potatoes, salt water, and in those cases, urine as well. So start to ask the students, what is the difference between plugging it into various different fruits? So here I've got now an orange plugged in, and it should be no surprise that I'm getting a very similar voltage. It's jumping around quite a bit because I've got a bad connection there. But when I start to get there, I've got close to 1 volt again.
Okay.
And we actually find that oranges produce slightly more because they've got a slightly more acidic component. And that's often something that surprises students.
Yes.
Okay, now lemons themselves have got a great deal of citric acid, but oranges have got ascorbic acid as well, which we all know is vitamin C,
Yeah.
which is adding to the acidity of oranges as well.
Okay.
So you can get them to make a variety of, fruit cells.
Yeah.
You can get them to make electricity from all sorts of things. And scientists are developing micro batteries this way to power devices inside humans as well, which is quite a nice example. So you implant a chip under your skin,
Yes.
and it monitors your blood glucose, but it also uses your glucose in an electrochemical reaction to keep itself alive,
Okay.
which is very clever. You never need to recharge it.
Shall we
So
move on?
again, yeah, absolutely.
Predict the outcomes of cells and measure the voltage of various spontaneous combinations.
Okay, so that we've already done here.
Yes.
Swap out the metals and ask the kids, what do you think will happen? Use the cell potential table.
Okay. electrolyze a variety of solutions after predicting products?
Okay, now that one's fairly important. What happens if I run electricity through this? What happens if I run electricity through that? Now, you don't always get two gases as products.
Okay.
In the one example, I got a metal and a gas.
Yes.
Sometimes I get two gases like I did with the chlor-alkali example. Now, they've got to be able to trace that back to the theory, and that's why you need to explore a variety. Why does electrolyzing sodium
So
chloride...
they don't think it's always the same?
Absolutely. I electrolyzed sodium chloride here, but I didn't make sodium. I made chlorine, yes, the same way that I did with copper chloride, but I didn't make any metallic sodium.
Okay.
So ask them why. What about this is different? And then start to investigate those.
Okay. Demonstrate electroplating, perhaps a leaf or a spoon.
There we go. Okay, so that's a very, very effective one. Actually changing the surface of a spoon is quite a cool thing to do. Try forks, knives, anything metallic. Keys work quite well as well. That's really, really nice to see a key turning a different color.
Yes, of course, not the electronic key.
Yeah, no,
Door
absolutely.
key would be fine.
Car keys are definitely a no-no.
Yes.
Those are electronic.
Yeah. And last one, make a small demonstration cell to show chlor-alkali levels. Chlor-alkali.
Yeah, the chlor-alkali cells. The one that we've got here with the indicators, I've chosen universal indicator to show the two different sides.
Okay.
One is alkaline, one is acidic. It actually demonstrates, and it's a physical way of seeing that I produce chlorine at the one and alkali at the other, and obviously the name chlor-alkali then becomes far more obvious.
Yeah.
It's a really nice physical way of seeing this, because to actually get them to go to see one of these plants is a really long day trip.
Yeah.
Most of them will never see how chlorine is made in industry. And here you're producing it on a lab benchtop, which really makes it real.
Yeah.
And, well, there's a multitude of others. If we had a lot more time, I could show you a variety of other ones.
Yeah.
Some of the others involve making electricity from... you could actually show them a hydrogen fuel cell. You now get demonstration kits where you can take hydrogen and oxygen. I'm sure you remember the explosion we had in studio.
Yes, I do.
Where that explosion is used to create electricity.
Okay.
And one of the things in the notes which I sent through was investigate electric cars. Where are they going to get their electricity from? And that's a really nice hook as well, because especially petrol and diesel cars, they've got limited time span. The next 30, 40 years, we'll start to see more electric cars. Where will they get their energy from? And this sort of chemistry is what's going to be driving them.
Yes.
Without a doubt, this is the only way to carry around energy with you. And at the moment, this is the only technology that we have that can store energy and produce electricity on demand.
Very interesting.
Yep.
Well, if you have any more teaching ideas that you would like to send us, please do. Send them to competitions@digitalclassroom.co.za.
Yeah.
We'll make them public, and then we'll choose winners from the submissions.
Yeah, fantastic.
Okay, thank you very much for coming.
Thanks so much, Helen.
This was very informative.
Good. I'm glad.
And thank you, Dylan, for your magic.
Okay.
We'll see you again next week. Bye.
Bye.